Okay, so welcome back. We're going to be having a qualitative discussion about the change to entropy of the universe. Because the change to the entropy of the universe is able to determine spontaneity. So in other words, it's able to decide if a process is going to be spontaneous in the direction shown or in the opposite direction. And it all comes down to one of two possibilities. If the change to the entropy of the universe is positive, then the process is going to be spontaneous in moving from reactants to products. However, if the delta S of the universe is negative, then the process is going to be spontaneous moving from products back to reactants. And in these cases, the process is going to be the change to the universe that's induced by the chemical reaction, which is, a very vague way of essentially saying, whether or not the chemical reaction gets to occur in the direction shown or not. And the third possibility, which is always there, is that the delta S, or change to entropy of the universe, would be 0, in which case then you'd be at equilibrium. So again, if this, then equilibrium. Alright, so we need to understand that the change to entropy of the universe is going to have two pieces to it. It's going to have the change to the entropy of the system and the change to the entropy of the surroundings. And what happens is we put them together to make this equation. So this is really what we're going to use to help us determine the spontaneity of a process. What we're going to use to help us determine the sign for positive, or negative for the entropy of the universe. And normally this is going to have to be done qualitatively. So for example, we'd be looking at something like this, which is considered a reversible process, and it would have a delta H of negative 92 kilojoules. So if we're looking at this equation, right now it's going to be really hard to say whether or not the system, whether or not the process is going to be spontaneous. And a portion of that is that we don't have enough information here to predict the sign for the change to entropy of the system, because we don't have any states of matter, which is really what we need to have in order to determine the sign for the change in entropy of the system. And in this case, everything is a gas, but that also means that because we don't really have numerical values associated with the absolute entropies of these substances, the best we're going to be able to do is make a general statement about the sign for the change in entropy of the system. Had we been provided with the absolute entropy values for the substances in this chemical reaction, we might be able to make an actual mathematical calculation for the change in entropy of the system, which would then lead us to an actual value for the change in entropy of the universe. But as it stands, we should still be able to make a prediction about the sign for the change in entropy of the system, remembering that the system is really just the chemical reaction. And as we have 4 gas parts on the reactant side and only 2 gas parts on the product side, there is a reduction in the entropy of the system, and so the sign should be negative. Now, when it comes to the change in entropy of the surroundings, we can apply the equation change in entropy of the surroundings is equal to negative delta H over T. Now, with the actual delta H value being negative 92, when we take the opposite of a negative 92, we're going to have an actual positive value for the entropy of the surroundings. And because temperature can have an effect on the outcome here, what we find is that at certain temperatures this process is likely to be spontaneous, and at other temperatures it's not. And so what has to happen is, in order for the process to be spontaneous, the value of delta S of the surroundings in its positive form has to be larger than the value of delta S of the system in its negative form. And if that's the case, we'll get a positive value for the change in entropy of the universe, and the process will be spontaneous in the direction shown, which essentially means moving from reactants to products. Now, if the value for the change in entropy of the system happens to be more negative than the change in entropy of the surroundings is positive, you're going to end up with a negative value for the change in entropy of the universe, which means that the process will be spontaneous as it moves from products to reactants. And if the two equal each other out, meaning that you have the same negative value, so same negative value, which I just said, as the positive value, it's just opposite signs, then you're going to have a delta S for the universe that's going to be 0, and you'll be able to say that the system is at equilibrium. So hopefully this helps you out. Oftentimes this type of consideration for the change in entropy of the universe is going to be qualitative, like we just did, but in the end it's going to help you determine spontaneity, remembering that positive for the delta S of the universe means in the direction shown, negative means in the opposite direction. So I hope this helps. Good luck putting it to use.